talking about transformation in open. So, transformation happens in OpenGL when we do transformation. Like if I have an object, then I move the object and I change the coordinate, or I rotate the object, or I scale the object, I make it small or I make it big. So this transformation comes under, so this kind of operation comes under transformation. So in OpenGL, OpenGL is a kind of mathematics, it's not physics. Like if I have a camera, the light falls on object and finally reflected light comes to the camera magnetic tape and then images are drawn. So whatever is in view, so those things, so it's a physics, angle of reflection and refraction and what's it? Okay, so OpenGL is not a physics, it's a pure mathematics. So like, so there are, when we draw an element, there is a light and object is there. Light gets reflected and it falls on OpenGL camera or eye, and then picture comes. So in OpenGL, when, so we are not talking about lighting now. So what about transformation? So object moves from here and there, and how transformation happens and how at the end what comes to the picture. So it's not that I can just in front of camera start moving any object and object will come in the camera. So that's not true, because there is a mathematics behind this. So there is a stages, there is a pipeline called transformation pipeline or a staging in transformation. So if I have a model, like I have a sphere, and it spans from -1 to 1 left, right, up and down and near and far, -1 and 1. Like that. So this is called how big the ball is, what is the actual coordinate of the ball. So that is called model coordinate. So model coordinate is the actual, if I place the model at the center, at the origin 0, 0, 0, what would be its dimension? So that is called model coordinate, local coordinate. So OpenGL starts from there. What is the actual dimension of the model, of the object? Now object goes in front of camera, so it will go if I translate, then object I rotate, then scale whatsoever it comes to my mind, whatever I do. So that is called a transformation in the sense that rotation, translation, or a scaling. So initially the model coordinates comes into the picture, or we call it vertex coordinate. So vertices, the actual vertex. So vertex coordinate, model coordinate, local coordinate, whatsoever. Then when it goes in front of camera, it starts doing the transformation here and there, rotation, whatsoever. So it changes the model view matrix. So the vertex coordinate, when it gets a kind of processed through model view matrix, then it becomes I coordinate, because this is what I am seeing through the eye. If it is at 0, 0, 0, I am not seeing. It is there where the camera is located. Now it is going in front of camera, so that it should come to the images should come to the camera. So whatever moving it is doing, it is modifying the model view matrix, and that whatever is coming to the camera or eye, it is perceiving that it is at distance of 10 unit and left, right, and so and so. In addition to the actual vertex coordinate. So vertex coordinate plus these transformation, model view transformation, it becomes I coordinate. Vertex coordinate processed through model view matrix become I coordinate. Now, this is what the real physics camera is. That's it. So camera is, model is in front of the camera, and that's it, that image is coming. But in OpenGL mathematics is beyond that. And now the model has to be inside the projection box, otherwise it won't won't come. So projection box again decide for the clipping. So projection, so if it is more left to the projection box or more up or more down or something like that, it would get clipped. So initial vertex coordinate get processed through model view matrix. Now it gets processed through projection matrix. So initially it was after model view it is I coordinate. Now after projection matrix it is clip coordinate. Okay. Now clipping is decided, means what is the object that is inside the projection box. So that will come. So this is next step. Now what about perspective division? Like if I go for perspective projection matrix, perspective projection where the near part of the model would look bigger and rear part, the far away part would look small. So again there is a change. Okay, so if I have a big ball, the near portion of the ball would look big and a rear portion of the ball should look small. The way it happens actually in the world, in the real world. So again there is a transformation in the coordinate. So first transformation was because of the model view, next was because of the projection matrix. Now next one is because of perspective division, because we are taking the frustum. So it's not a kind of ortho, it's a perspective. So it would come to kind of normalized device coordinate, I coordinate, clip coordinate, after perspective division, normalized device coordinate. Okay, so finally we are done. Means what would be the actual shape of the object that we need, the camera can see. So that is the normalized device coordinate. Okay, so that came after the perspective division. Model view matrix, projection matrix, and perspective division. So we have normalized device coordinate. Now that those vertices, finally it is falling on the camera rail, camera magnetic tape. How big is that? What is the size of it? So that is called viewport, kind of viewport transformation. So my camera rail is twice the width of the height. So full image would be transformed like that. My camera rail is twice the height than the width. It is like that. Or the camera rail is equal in size, width and height. So full image has to fit in the magnetic tape. So that is called at the end it is called viewport transformation. So what we get in the camera, because so we have the actual model, like football or a sphere we talk. Then after the translation, after the model view transformation, then it became I coordinate. After projection matrix, it became clip coordinate. After projection matrix, then we have perspective division, and it became normalized device coordinate. Finally, it falls on the camera, and actual image is dependent upon the kind of width and height of the, or we can say geometry of the actual magnetic tape. So that is called viewport transformation, and the end coordinate that comes into the picture, that is called window coordinate. So we have vertex coordinate, then I coordinate, then clip coordinate, normalized device coordinate, and finally we have window coordinate. So this is the transformation pipeline that we actually see on the screen. So now after that we'll discuss various parts, what is the vertex coordinate, and then transformation. When we go from model view transformation, model view matrix, then again it is a kind of little complex, and there are two ways we can understand this philosophy of OpenGL, like fixed grand coordinate, or grand fixed coordinate, or a local coordinate of the. So how translation happens, rotation happens. There are two philosophies. When the axes are fixed, that is grand fixed coordinate, or the axis x, y, z or whatsoever, that is local to the model, not fixed. So axis is would the XYZ axis would change. So local coordinate, but at the end drawing would be same. But and the way we understand is there are two keys. Then it goes to projection. Projection can be kind of two types. One is ortho and one is kind of perspective. So then we'll go to, if it is perspective, then we'll go to perspective division. At the end, we'll see that how viewport geometry, width and height, it plays the role in the final shape of the model. So that we'll see. So this is the various stages in transformation in OpenGL 3D. Further to discussion on various stages of transformation. So we'll proceed on desktop. This is Linux Mint. Okay, so what we would see is the stages of vertex transformation. So transformation of a model like translation, scaling, rotation. So these are called translation of a model. Model is kind of is changing its shape, it's changing its location. Okay, so what is model vertex? And projection matrix, model view matrix. In projection, we'll talk about orthographic and perspective projection. And finally, we'll see the magic of viewport, what it is. Okay. So, if I talk about the stages of vertex transformation, the first stage, that is the vertex XYZ. Vertex XYZ, the coordinates of the vertex. So if I have a model, then what are its coordinates? It is kept at the origin. So that is the vertex coordinate. Model view matrix. So that comes into the picture when we do the transformation. So when we do vertex, when model is drawn at the origin, then it is have movement, rotation, scaling, whatsoever. And if it does so, it modifies the model view matrix. And whatever the new coordinate is, that is called I coordinate. Coordinate at the origin, transformation happened, then from the camera point of view, at the camera point of view, it is at origin. Now, it is not at origin. What is its new location? That is I coordinate from camera point of view. And then projection matrix. So when it goes inside the projection, the model view, then it may see the clipping, means it has to be inside the projection box. So if it sees the clipping, then a new coordinate would come into the picture. So that is called clip coordinate. Okay, if there is no clipping, if there is a clipping, whatever, the resultant coordinate then falls into perspective division. So perspective in the sense that object would look bigger when it is near to the camera, and it will look small when it is far away from the camera, the way we actually see in our life. So in that way, coordinates changes. If I translate the object near to the camera, it becomes big, so its coordinates changes. So new coordinates come into the picture after perspective division. That is normalized device coordinate. So normalized device coordinate. So after perspective division is done, then x, y, z. We don't need z as kind of z would be transformed in x and y only, because the magnetic tape inside the camera, that is only two-dimensional. So normalized device coordinate in the sense that z will be gone and whatever we have kind of absolute value of x, y, z, that will be divided to x and y. Finally, it would come in the range of -1 and 1, and in the width, in the kind of left, right, and again -1 and 1 in the kind of bottom and top. So that is the kind of normalized device coordinate. Once we have the coordinate in x and y in normalized fashion in the range of -1 and 1, both in x and y and bottom and top, then we come to view transformation, viewport transformation. The viewport transformation is how the camera really, if width is twice the height, because image has to fall everywhere, or height is twice of the width, or it is square. So it is like we did all the magic, and if viewport coordinates, viewport geometry is not perfect, then probably image would not come nicely. So whatever the kind of mathematics we do in the view transformation, finally it comes into window coordinate. This is the coordinate that we see. So from model kept at the origin and its own coordinates, to the transformation, to the projection box, to the perspective, and then finally to the viewport. Whatever computation happens, then finally we see the window coordinates. So this is typically transformation pipeline of various stages in the transformation. Okay, so idea is okay. So idea is that how rotation happens. So like we'll see the translation is easy. Like if I move this cone into -z axis, then it will move in -z like that. But rotation has some fundamental. Okay. So how we decide the axis? Like if I have a cone at the origin, then which will be y-axis, x-axis, and z-axis. Okay. So we have to kind of put our right hand like this, and if this finger is y, then this would be x, and middle finger, that would be z. It is exactly like that. If this is y, this is x, then this is z. This is how we decide for the axis. What about rotation? So this is how we decide for the axis, and this is the way translation would happen. Rotation is, we have to right hand palm, we have to kind of fold in a way that thumb, if thumb is in a particular direction, then the way the fingers are, that is the movement. So if thumb is in this direction, the movement will happen like this. Okay, it, you can think in clock or anti-clock whatsoever. Like if I have a new axis, so this was x-axis. If I have a new axis x, y, z, I mean new vector. So this is a vector that is kind of beginning from origin, and this is my right hand. And if this right hand, the thumb is pointing toward the vector direction. So this is vector direction. This is the arrow is the vector direction. If I make a positive rotation across this new vector, then it would move like this, fingers. Okay. So if I do rotate 30 degree and with this vector in mind, then it would rotate like this. If I rotate 30 degree with x as a vector in my mind, then it would rotate like this. If I rotate in negative way, it would rotate anti, opposite, like this. So this is, so for translation, simple. the axis, the way we choose is this is the fundamental, and rotation we do like this. Okay, now we'll move it to so uh, okay. So now we'll move to model view matrix. Okay, so model view matrix, first object need to be kept at the origin, and then we'll proceed with the transformation. Okay, so there are two way of okay, we'll talk about two way. Now let's see the transformation, what we actually want. So I have a code, and that is like this: GL translate, scale, rotate, translate, and then draw the model. Okay, in actual mathematics, this happens in reverse way. Matrix multiplication happens in reverse way. So in actual mathematics, so I think we can. Six, seven. Okay, so in actual mathematics, if I have a cone, if I have a model, and we have the matrices like this, so this is actual mathematics. If I have a vertex and I have rotation, translation, and then scaling, multiplication happens in reverse direction. Vertex get multiplied by R, then T, then S, and that is the transformed vertices. So STR we write as a model. Okay, so model kind of matrix. So it happens in the reverse way. Okay, so now we'll proceed here. Now this is the code that we need to understand. GL translate, scale, rotate, translate, and then the model. So it would happen in reverse direction. This is the actual mathematics. So cone would be drawn, it would be translated, rotated, scaled, again translated like this. GL begin, GL point, and this is the model drawing kind of a program. And then uh, multiply GL multiply matrix with the translation, rotation, scaling, and translation again. So and then above. So if model view matrix is loaded, load identity, it won't go like this. It will go from bottom to up. This approach is the actual mathematics. So it is called grand fixed coordinate approach. So we are here. We are vertex drawing and model view matrix. Okay. So vertex is drawn. So now model is kept at the origin. So model is kind of this whatever the dimension we are placing on the model, that is the actual dimension of the model. So that is the called vertex object coordinate. So this is the object coordinate. This is the object coordinate. Right now, in this diagram, this is the object coordinate. Now, object is translated 5 in the y direction as the course is 0, 5, 0. Then rotated in minus 90 and across z direction. So if this is z, Minus 90 means it will rotate in this fashion. Okay. The way talk about rotation. So right hand thumb and pointing to Z direction. So it would go, if it is positive, it would go this side, negative, it will come this side. So first it is translated, then it is rotated, then it is scaled. We can see that the scaling is not smooth. 0.5 along x-axis, 1 and 1 along y and z. So 1 and 1 along y and z, there is no scaling. Well, scaling happens only in x direction. So the position of this model along z axis, since it is we are scaling by half, size would become half and this distance would also become half. So earlier this distance was 5, this is 5, so this is 5. Now this will become 5 by 2 because along x axis we scaled. So this will become a small and axis should also scale for a moment. Now we are translating again 4 4, so it is going up. So new, so at the beginning its position is 0 0 0. Okay, so at the beginning its position is 0 0 0. Okay, so initially it is at 0 0 0. Okay, so initially it is at 0 0 0 and at later stage this came to 5 by 2. 5 by 2 became because of scaling plus 4 because at the final stage we translated again 4 4 0. So x is 5 by 2, 4, y is 4 and z. We did not do any movement in z direction. Okay, so what is the point? Why we say grand fixed coordinate? The coordinate x, y and z, this coordinate is not moving. Whatever we are doing, that is in the global coordinate only. What we have only one coordinate, that is x, y, z. Now model is moving. Okay, our coordinate, our with in reference to our coordinate system. Then model is rotating in reference to our coordinate system. Then model is scaling with reference to our coordinate system. Then model is translating again with respect to our coordinate system. So this coordinate system y, z and x, this is fixed. It's not changing. This is actual mathematics. So whatever transformation we are doing in reference to fixed coordinate. Okay, so this is bottom to up approach and this is the real mathematics. Matrix multiplication happens from bottom to top. Okay, now so this is called grand fixed coordinate. Now we are here, we are talking about model view matrix. First we draw the model at the origin and then we start doing the translation, we start doing the transformation. So this transformation, what we did, this is natural way of transfer. Okay, what is problem here? What about this? What about this? I translated here and here I want this to be rotated like this. Okay, I can't do this because it would rotate along the axis, not its own axis. We are trying to rotate along its own axis. Okay, so this is not possible in this fashion. Mathematics is same. We are not going to change the program, but the way we are thinking is not possible. I can scale. After scaling, I cannot rotate. What I can do, if I want in this fashion, what is the solution? If I want to scale and then rotate, solution is I have to rotate here only at the beginning. Okay, and then I can scale. So that is the solution. Okay, so in this approach, what we are talking in the fixed grand coordinate, at runtime when I have scaled, at runtime I cannot rotate. I have to rotate along the axis. Like if I rotated along the z axis, okay, it took this distance. Okay, from this is z axis. It took this much distance and rotated across z axis. That is the problem with this approach. Means local origin, local axis rotation is not possible. It's possible the way I showed. Okay. New approach comes. So we are here only in the model view matrix. So in the new approach, it's called moving local coordinates. Program is same. Program is same. Whatever we are talking, it's only kind of hypothesis. There is no change in the program. Our program is same. Now, the way we have written the code matrix multiplication, okay, so actual matrix computation happens from bottom to up. Can we think of top to bottom approach? The way we should think. The actual mathematics when program runs, then matrix multiplication happens from bottom to top. No one can change this. What about this? Earlier we went, so the way program computes, we also thought in same way, bottom to up. Can we think top to bottom? Okay, first translate, then scale, then rotate, then translate, then draw the cone. This is called moving local coordinate. That was fixed grand coordinate. Okay, this fixed grand coordinate, the actual XYZ coordinate would not change at all. But in the top to bottom approach, we will change the coordinate. Okay, there is no fixed coordinate. Now, this is the beginning stage. After this, I do scaling. I do GL scale, 4, 4. So X and Y direction it moved and it came to 4 and 4. It is above the Z axis because there is no, it is in XY plane. So there is no movement along the Z axis. So it is 4 and 4. Can we see there is a new axis coming? It is not missing here. Okay, there is no new axis, but here there is a new axis, new y axis, new z axis, new x axis, and new z axis. This new axis is local to the model, and this model is not dependent upon this axis, this fixed grand axis. So this concept is gone. This fixed grand axis can be thought as it doesn't exist at all. Okay. Now it has got its own axis, local axis, which has y coordinate, y axis, x axis, and z axis. So first it translated 4, 4. Now it would scale 0.5, 1, 1. So it is scaled in x direction, y direction, and z direction. It is exactly same. And the scaling, the scaling happens in x direction. Now if I move into x direction, the scaling would take effect because x-axis is local x-axis is scaled. Okay, so diagram should be actually like this. Okay, so there is no change in y and z axis. So y and z axis should be same height. Okay, it is as big as it was earlier, and z axis also. It is as big as it was earlier. Okay, x axis is small because there is a scaling in x axis. So local axis concept scaling happened, x axis has become half. Okay, otherwise there is no change in other axis, so all are like same. Okay, so z axis same big, y axis same big, but x axis is small now because it is scaled. If I move along x axis, the model should also start scaling because that axis is small. If I rotate across, if I rotate and it comes in y direction, no problem. If I rotate and it comes in z direction, no problem. If I rotate and that comes in x direction, x axis direction, it would start scaling because axis is small. So this is kind of a different way of same hypothesis. Top to bottom, that is called moving local coordinate. Now model has its own coordinate. Model had its own coordinate, and first it got translated. Now x axis got scaled because if I see the scaling, then x is 0.5, y and z is 1 1. So x got scaled, y and z are same. Now we are rotating along z axis. We are rotating. Okay, so rotation happens, but it became smaller. Earlier it was big. Okay, it was tall. But if I rotate along z axis, it is rotating means in the side of x axis because rotation happens along z axis. This is the fund of rotation. If I rotate along z axis, means my thumb, this thumb is here. Okay, so if my thumb is here, then this item would rotate along z axis. It's a kind of I have a stick, and a stick we are rotating. See, if I stick, if this is the stick in z direction, if I rotate the stick, then model would rotate. Okay, so model not only rotated, it became a smaller also because in x direction there is a scaling. So this is the problem with this approach. Okay, so if it is not uniform, like if I had a scaling 0.5, 0.5, 0.5, then all three axes would be scaled by half, and then it is easy. Now it is not kind of orthogonal. Means whatever we see along the x-axis is different, and what we see in along y and z-axis is different. So our axis is not highly orthogonal the way it is to be. So be careful. And now after rotation, we did translation. So this is the scenario of rotation. What is good about the rotation? It rotated there itself. If I see the grand coordinate, and if I rotated along z axis from here, it came here because it is rotating along the fixed z axis. But here, if I rotate this guy, it would rotate there only. because it has local coordinate system. This coordinate system has no meaning. Okay, someone can actually erase this. So it rotated across. Now after rotation, we translating along the file. So this green is new y-axis. This green is new y-axis. So now it would move in this direction. Okay. So what would be the final coordinate? So this is 4 4. Then scaling happened, and then rotation happened there itself. And now the movement in x direction would be half because we scaled it, even though we are moving in y direction. So initially it was 4. Now we move 5. So it would be 5 by 2 because we have scaled it, and other is 4. So 4 plus 5 by 2 and 4. Okay, it is exactly same, 5 by 2 plus 4 and 4. So whatever we get at the end, whatever is beginning, and whatever we get at the end, it is same in both approach, because after all OpenGL code is same. But the way, so here it is here it is at the same location. So this is transformation. Transformation can happen from bottom to top. If we take the coordinate as a fixed coordinate, or it can be local coordinate also if we go top to bottom. What someone feels easy, that is the kind of, it is his mentality. Okay. Okay. So this approach, generally people find it easy in the sense that they have to think only at the local axis, not at the grand axis. So local axis, rotation, translation, and scaling, everything happens in local axis. So this is easy, but this is not the actual computation that happens. But whatsoever, we get the same result. Okay, so next in our pipeline is projection matrix. So model view matrix. So we did the transformation, and transformation happens through two concepts. One is fixed grand coordinate, and one is moving the local axis. Okay, so in local axis, we can actually forget this the way I am saying. So it is like there is no local axis. Okay, so I can just forget this. There is no local axis at all. Now this object has its own axis. So local this grand axis is gone. Only local axis exists. The whatever we had the fixed axis, that is gone. That has no importance. So it can be considered in this way. So this is local axis move. Local axis is coming into the picture, and it has the kind of actual presence. Okay, so we'll move now to projection matrix. So in projection matrix, when it moves, like if I have an item, if I have a model must be inside the projection box. So projection box, I have three models. One model is kind of on the edge of the projection box. So if I see from the camera, it would look like this. Okay, so one is clipped there because it is not well inside the projection box. So whatever the new kind of the coordinate whatever we see. So here at the beginning object is at origin. Now it moved and object is here. So whatever we see, this is called I coordinate. That is 4 plus 5 by 2 4. So this is the I coordinate, and so camera sees in I coordinate. So camera is saying the object is here, but it's not necessary that object will be drawn because object must be inside the projection box. A clipping happens, then this is the new coordinate of this object. So right part and bottom part is gone. So this is called I coordinate. Okay. So we are here. It must be inside the projection box. Otherwise, clipping coordinate will come into the picture. Okay. Perspective division, like if, okay, so this projection box can be a cube or it can be a frustum like this. Frustum in the sense that it has a near plane and it has a far plane, okay, and an object would behave like this. If object is near to the camera, it would look big. If it is far to the camera, it would look small. Okay, here it is near to the camera or it is far to the camera. There is no change in the coordinate. But in the perspective division, if it is near to the camera, if it is far to the camera, the coordinate is changing. Okay, so typically this kind of matrix would come into the picture, and whatever the new coordinate what we achieve, that is called normalized device coordinate. So this is the final coordinate that will go on the magnetic tape inside the camera. Okay, so if we see the real world camera, then it is up to model view matrix only. Projection matrix and perspective division, this is something that it is kind of OpenGL computes. And finally it go to the viewport. Viewport is the camera reel. Okay, so on my computer this is the viewport. On viewport, what will happen? So if we have x and d and y and d is a normalized device coordinate, then if viewport width is this, viewport height is this, and this is the origin. So okay, so this is the origin. Okay, so this is x and y. This is x and y. Okay, so this is x, this is x and y. Okay, so this corner left is x and y. I think I can do it better way. Okay, so this is x and y, that is the bottom left position. So in OpenGL, origin is this direction, not like typical windowing system where origin is top left. Origin is bottom left. So this is x and y. So typically it would be 0, 0. But if I place x and y, then plus x and y, whatever the width of the viewport, whatever is the height of the viewport, and whatever the device x and y what we received, so this would be the xw and yw. Okay, so okay, so okay, so if this is my computer screen and this black portion is the camera rail, then bottom left xy is the kind of origin of the camera, is the camera rail, and this is height, and this is width. In that sense, if I have received from the previous computation, so from here I have received this. This normalized in the sense that all the coordinates are in -1 to 1 and y. So x is -1 to 1, y is -1 to 1. This will get mapped to the actual window where bottom left is xy and this is height and this is width. And then computation would happen like this. Whatever x normalized device coordinate, whatever y normalized plus 1, height by 2, width by 2 and x and y. Whatever comes, okay, that will be xw and yw. So, if this is 0, x is 0, means our coordinate is at center, if it is -1 to 1. And if I am talking about this location, 0, 0 from both directions. So if it is 0, then it would happen width by 2, height will be height by 2, and xy is also 0. So our model would be drawn at the width by 2 and height by 2. That will be at the center. If it is 1 and 1, so 1 in x is here and 1 in y is here, that is top right. So 1 and 1, that will become 2, so that will be width and height. So it will width and height in the sense it will be drawn at the top right. If it is -1, bottom left, so -1, it will become 0. So both are 0. If both are 0, then it is here. Okay. So this is about the transformation, vertex transformation pipeline. So once vertex is drawn, it is transformed, then it goes to projection matrix, then it goes to perspective division, then finally to the viewport, how it is mapped, whatever the normalized device coordinate what we get, how it is mapped, so that it would be the final window coordinate. Okay, so we have lot of lab session here. We have UML design, then model view matrix, projection matrix, perspective division, viewport. Finally, we'll build up a solar system, like Earth is moving around Sun and Moon is moving around Earth. So that we'll see in the lab session. So in the lab session, like we'll write a package. So in Python, it is package. So we'll write a package or we'll write a module, and that module would use OpenGL util. So we have a kind of a library package, and that reads a .obj file. This is UML diagram. And in that lab session, we'll also use Python 3 OpenGL library. Okay. So this library has OpenGL code, and this has our own code to draw, shape and read the .obj. That is a kind of Blender. A Blender is a tool that brings the .obj file. It would read and it would kind of create vertexes. That vertexes finally will be drawn. So this we will develop lab session. If I talk about OpenGL util, it has mainly two classes, shape and util-c, and then we do generalization of the shape and to have the other classes. So this is the UML diagram. Okay, so first we'll see the local coordinate. So local coordinate final movement is here, and grand fixed coordinate also final movement is here. Okay, so grand fixed coordinate it is here, and in moving local coordinate it is here. Final end up result is same, that we'll see. So we are talking about everything in perspective. Now what is orthogonal? Let's see two items at same location. So orthogonal would show like this, perspective would show like this. There is a vast difference because it is far away in z along the z-axis. If it is far away along the z-axis, the item would appear small. It would appear tilted as per the first term. Perspective is not cube. perspective is first. So frustum in the sense that item would look rotated also. So this is what item would look if it is a kind of placed in minus z direct on minus z axis. But where is orthogonal would look like? So we'll see actually. Our claim is right. Okay, so we'll do some kind of magic with the viewport also. Like if a viewport is 0, 0 and W and H, window width and height, it would look like this. If viewport is kind of, uh, uh, if width is width by 2 and height is height, so width we are decreasing. Whatever width we are getting in the from the operating system, we are dividing by 2, and then we'll shift x to some location. It would appear like this. Appearance is changing, so final coordinate is changing. If I change the viewport, if I modify the viewport, object would look different. So this is very crucial thing. It's not a kind of easy way. This portion also changes viewport transformation. If I specify different kind of viewport, then this would change. Okay. Now height is half, width is same, height is half. Here width is half, height is same. It would look like this. Width is half, width is same height. So it would look like so. Viewport also changes the magnetic tape geometry also changes it. So this is what we will see in the lab session. So in lab session we will develop this lab session package, and then we'll see the grand and fixed coordinate that would come in the model view. Then projection wise we'll see orthogonal and perspective differences, and then we'll see the viewport. So this is this portion of lab session. Human design, model view matrix, projection matrix, perspective and viewport. Then we'll develop solar system. Okay, so we'll install the OpenGL first. Okay, so it is already installed. Now, so we'll develop, so we already, so we'll create a directory. Okay, so directory is empty. We'll have kind of OpenGL transformation stages .py. Import everything from OpenGL GLE, import everything from OpenGL.glut, import everything, import RE from OpenGL util. So this is a library file we have. We'll import util C and shape. Okay, we'll have shapes list, that is global list, and we'll have a global, and we have cone. So cone example that we are giving. transformation. So we have a transformation list of dictionary. So we have X. So this is a transformation is a dictionary, and so X for X in shapes. So this is a dictionary where each key is the whatever we have in the shape. So in shape we have two, global and cone. Default shape is global. Okay. Coordinate system is grand coordinate system, that is the default. We have to change it to whatever we want. Now we'll have in it the way we generally have in OpenGL. So GL clear code, clear color. GL shade model as GL smooth. I think we're done. Now we'll have function called display. So in display we'll have GL clear, GL color buffer bit, GL depth buffer bit, GL color buffer bit, GL depth buffer bit, GL push matrix, GL translate. Okay, so at the beginning only we will translate to -5. GL push matrix, GL translate. Okay, I cannot do kind of formatting or indentation. It is Python, so we are bound to the way Python wants. Okay, so we'll make it translate F, and we'll have GL translate X if len X equal to 3, else GL rotate. Okay, so somewhere I'm putting F, somewhere I'm not putting F. I think it should take care X, if not X 0 equal to S, else none. So this we'll see for X in transformation global. Okay, so this is the code we are writing. GL translate X if len of X is 3, or GL rotate X if not X equal to S, else none, X in transformation global. GL line width will keep it 1, for I in zip. Now we are drawing the axis. This global axis. We are drawing this global axis. Okay. And we'll draw the local axis also. So global axis we are drawing. So that is minus 0.5 to 0, 0 to 1.0, 0, 0. So we have drawn x-axis minus 0.5 to, so left side we have made it is kind of less long. Now y-axis will do similar, minus 0.5, 0 up to 1.0, 0. Z-axis also will do the same, 0, 0 minus 0.5, 0 minus 0.5, 0, 0 minus 0.5, 0, and 0, 0, 1.0. GL begin GL lines. GL color 3F, and that would be star I1. Okay, so what we are trying to do is, in the practical session, so this axis we are drawing. So y is big, minus y is small, minus x is small, plus x is big. So this axis we are drawing. So minus 0.5 to 1, minus 0.5 to 1, minus 0.5 to 1. So this is what we are drawing. Now color would be the first one. So I think we have not drawn the color. So that we have to declare. Okay, so we'll modify and we'll write the color. So this we are here. So we'll add the color. So color is, first is red, then it is green, then it is RGB, then it is blue. Okay, so I think, okay, nice. So first is okay, so first is the coordinates of the line, and next is its color. We zip it, and then we okay, so we'll okay, so we'll proceed now writing the code. So GL vertex 3F star I0 0. Okay, so vertex we have drawn two vertex this 3f star I 0 1. Okay, so from 0 to 1, now we have the GL end. For L shape in shapes, GL push matrix. Okay, so we'll do the magic. So GL translate star x if len of x equal to 3, else GL rotate star x if not x 0 equal to s, else GL scale. So we'll scale star x 1 from 1, GL scale from 1 onwards. Okay, so for x in reversed transformation L shape, if coordinate system G equal to grand, else transformation. I think we can keep it short. So probably we'll see the local coordinate first and then we'll see this. So we can curtail this. So GL translate x, rotate x is equal to GA, otherwise 1. Okay. For x in transformation S, okay, if L shape not equal to global. So for not global, we are writing this. So this is the code for x in transformation L shape. Whatever L shape is coming, in that L shape we rotate if it is 3. Otherwise we rotate if it is 4, because in rotation we have 4. In scaling also we have put one S, because scaling and rotation both have 4 kind of list size. So x0 S derivative you are putting. If it is S, then we'll scale 1 to the end. Okay. For x in the transformation L shape, if L shape not equal to global, so only for this item. Okay, so we'd proceed now. So if L shape equal to cone, if coordinate system G equal to local, so first we'll show the local GL line width. So we'll do the same thing what we did. So we'll draw for the local, we'll draw the coordinate system again. So if it is local, then GL, I think we can copy paste, 3, 4, 5, 6, 7, 7 and we can paste it here. Okay. So if it is local GL line width, we'll keep it 2. And now we'll draw the local coordinate. So this would differ. So it is 0.3 minus 0.3 to 0.5. Similarly, this is minus 0.3 to 0.5. This big it would be. Similarly, this would be minus 0.3 to 0.5. Okay, so minus 0.3 to 0.5 and minus 0.3. Okay, so x-axis is minus 0.3 to 5, y-axis is minus 0.3 to 9. So I can make it bigger, y-axis. Okay, it is up to me. And then z-axis is minus 3 to, or I'll keep it 0.5 only. 0.3 to 0.5. What about colors? So color would be, okay, so it would be dark 1, 1, 1. Okay, so now we have GL lines the way it is, and I is 1 and then 0, 0 and 0, 1 and GL end. Now this is local vertex we have drawn. Now we'll draw the cone. Okay, so we'll draw the cone. So after GL end, so coal color will set. So okay, so where this Mr. Cone would come, this is problem with the Python, means we have to kind of okay, so we'll say GL color 3F and color of the cone is purple and GL rotate minus 90 0 1 0. So along x-axis we are rotating it so that it would look the way we want. Then glut solid cone, and that is 0.2, 0.8, height is big, and 40 and 32. Okay, so this is the code. I think I am done. Now we'll do pop matrix. GL pop matrix, GL pop matrix, GL flush. Okay, now we'll have def reshape W and H. We have global transformation, GL viewport, So GL viewport is this, and GL matrix mode, GL projection, GL load identity. Now we'll have GLU perspective 40.0, width y height. This is what we are considering. Okay, or we can say width y height if width is greater than equal to height, else height y width 1.0 and 10.0. This is the limitation. We'll have GL ortho also, GL ortho minus 1.5 to 1.5 minus 1.5 to height by width minus 1.5 into height y width 0.1 to 10. Okay, so we can make it 1 to 10 the way it is. If width is less than equal to height, else GL ortho minus 1.5 minus 1.5 into width by height 1.5 into width by height 1 to 110. Okay, so we have GL matrix mode, GL model view, GL load identity. Okay, so if we reshape, so at that time we can have transformation equal to, it is up to me if I like to reinitialize everything here for X in shapes. I can comment it also. Okay, now we have keyboard. Keyboard key XY, global is transformation, we are changing this. Shape, shapes, shape, global coordinate system G. Key equal to, will explicitly convert it to bytes. If key equal to B tab, shape equal to shapes, shapes dot index shape plus 1 len of shapes util c dot pretty print that something has changed. So if we print, so it would say keyboard new shape. Okay, so this is the grammar for the pretty print that we have written. So in the pretty print, we are passing one dictionary. It has a key that need to print it. It has a value that is the shape, and it is taking two stars. So we are kind of dereferencing it. If R is search, G and G, key dot decode. Okay, then global system will change it. So kind of coordinate system underscore G equal to grand if key dot decode equal to G, else it is local. Okay, so we'll every time we'll convert it to local, because right now we have code only for local. Glut post redisplay will force the redisplay function to be called. It is quite short. If name equal to main, glut init display mode, glut single, we are still using single, glut RGB, glut depth. So in this mode we are initializing it. Glut init window, size 500 by 500, glut init window position. So we'll keep it as at 100. Glut create window, my OpenGL code init glut display. So for the display, this is the function will get called. Glut reshape func for this will get called. Glut keyboard for this function will get called. Glut main loop. Done. Okay, so we have written the code. So we'll analyze it again. Okay, so I have imported from OpenGL util. So we'll copy OpenGL util. Copy OpenGL util here. So OpenGL util code is quite simple, and it has class utilc, and it has function like normalize, get normal vector, display. So display would actually call the display, and display it is in two mode. So what we want for the display, so in one mode we go for the traditional GL begin, and in other mode we go for the draw array. Okay, so this would be first. Then we have buffer for trimming something. Then we have keyboard. In keyboard we catch the keyboard, and if it is a kind of if it is XYZ, then we make the translation in XYZ. It receives transformation dictionary that it modifies, and if it is left right, then it will go left right. It will rotate along the XY. If it is S, then it would scale. It should scale in 0.5, but for this example we can make 0.111, this is, and okay, then we do the kind of some final transformation. So if we are doing kind of 2-3 translation in continuous fashion, so we can trim the transformation matrix. So transformation matrix get changed in place. So in Python we get the reference, so that reference only we are modifying. Pprint, and then we have another class called shape, so we have imported this also, and shape shape is in two way. One is normal way, and one is if it is kind of draw array, if we are using. Then display, we call display, so this is the display. We can derive from the shape, like pyramid is derived from the shape, and that's it. So this is the, so if we see the design, then shape is open for the generalization. So where we have generalized in as pyramid, okay. Okay, so here it is pyramid. Okay, we can go for more generalization also. Okay, so this is the idea. Okay, so these two the classes that we showed. Now we'll walk through this. Now we have from OpenGL util, we imported util C and shape. We have shapes list. So initial is the global. This is the global rotation, and this is the for the cone for the model. Transformation, for every shapes we have a kind of a list of transformation, like translation, rotation, and scaling. So for each shape it would have a list. For x in shapes, initial shape is global, coordinate system initial is grand, init we clear the buffer, and shade model is smooth. So in display we clear the color buffer bit and depth buffer bit. Push matrix we translate minus 0.5, so we push the kind of projection matrix. So here, so projection matrix, so this is the actual axis, so this axis would move now to this location 0.5, so that it will be inside the projection. So projection we have pushed to minus 0.5. Then we do GL translate x if len is x, rotate x if not x equal to x0 equal to. So if I see this code and keyboard, then for scaling we are also making 4 length list. These are the scaling, and first is S. Okay, whereas in rotation anyway we have 4. So in rotation we can see first is the angle, and next is kind of XYZ. So in scaling also we have done S. So we should differentiate somewhere. So here we are differentiating that we translate or will rotate if it is not x0 equal to S. Otherwise we do nothing. Transformation global, line width 1, and then we draw it. Now we go for each shape. In shapes we push the matrix and we'll do the translation, rotation, If it is scaling, then we go for the scale, and 1 0 because S character we just omitted. And for X in transformation L shape, if L shape not equal to globe. If L shape equal to cone, okay, now we are iterating in the shapes. If it is cone, then we are drawing the, okay, I think we can go for okay, so we should go for general drawing, not only for cone. That should be the idea. Okay, so if L shape is cone, okay, so we are drawing it. I think it is not a good idea because we should draw for everything. Okay, okay, let it be like this because otherwise we iterate, keep iterating, and it is kind of so where I can place this, because it would kind of draw every time. Okay, so we'll move it out. 7, 8. Okay, so we always draw the line. Okay, now we are iterating through shapes, and if coordinate system is local, then it's a good idea to draw the, okay, okay, so I think we'll keep it there only because it has shapes for the cone. Okay, so what I can do is, okay, I'm sorry. Okay, so the reason why it is inside the cone probably is because it has the kind of coordinates for the cone. Okay, so if it is L shape is cone and coordinate system is local, so no problem, we can go ahead and we can kind of do the magic. Now we can place it here. Okay, now rotate and we draw the cone. Once we are done, then we can pop the matrix. So if shape equal to cone, okay, so if our shape is cone, okay, whatsoever, since we have done the push matrix above the shape, okay, for every item we have done the push matrix, we will do the pop matrix. So push matrix for every shapes, and then we'll do pop matrix, then finally pop matrix for the global, what we had done the push matrix, and then GL flush. So in reshape we have done global transformation because we are resetting it, and viewport matrix mode, global identity, GL perspective, we have set angle as 40. So this angle is this angle. This angle is this angle. So if frustum, when we create the perspective frustum, that we set the angle. When we create the ortho, then near plane, far plane, left plane, right plane, bottom and up. That is the cube. Whereas in the perspective, the near angle first is required. At what angle we are seeing? So this is 40. Okay. And then width by height, else height by width. So this is the kind of width and height ratio that we are putting. And then near and far, this near and this far. Okay. So width by height, kind of left, right, and up and down. So this is so up and down is top and bottom is covered by 40-40. Left is covered by width by height, left and right, and near and far is 1 and 10, like in GL ortho, minus 5 to 5 left and right, okay, bottom to top, near and far. If width is less than height, if width is greater than height, minus 0.5, width by height 1.5, width by height 1 to 10. Okay, model view, a load identity. Transformation matrix will, whatever we have set, will reinitialize if we reshape it. And in the keyboard, if it is tab, then we'll move to next shape. So shape we have a list. Shape we have a list. Initially it is global. If we keep pressing tab, it will go to next model. So global is not a model, it is a global axis, but we have put it here only, and where scaling and those things are not allowed. And in cone, if I press tab, it will go to cone. If I press tab again, it will come back to global. So that is the keyboard. So if you press, then shapes dot index shape whatever +1 and length of the shape. So that way it will keep moving. And we did the p print. Okay. I think V is missing. That is highly important. Okay. So we'll put Mr. V. If key equal to V, we want to kind of verbose printing. So util C dot pretty print, and in pretty print will print like shape equal to shape transformation equal to transformation. So this is the whatever we want to print, we can just put in this dictionary. Like I want shape, then shape. I want transformation to be printed, then transformation. Okay. Now if it is G and G, then coordinate system will make it grand if it is G, otherwise local, and glut redisplay. Okay, so this is the code. Now we'll go to main, and here in the main, okay, it's a kind of main function, and glut init display mode. So glut single RGB and depth, glut init window size, glut init window position, glut create window, init glut display func, glut reshape func, glut keyboard, and glut main loop. So our code is complete. I think we can try. Python TS. Okay. So GL begin. Okay. Glut keyboard is wrong. So glut keyboard 80. So glut keyboard function is keyboard. Oh, okay, so it is coming. That we can see. Okay, so we'll go through the live session. We can rotate axis. Now, if I press V, then it would print the current stage, and shape is global, and global and cone both list is empty. So if I press X, okay, so it is not moving. Okay, it is not taking the keyboard at all. Okay, glut keyboard func is keyboard. Okay, we have def keyboard. So pressing the keyboard is taking, but keyboard is not happening. So this proves that we are not calling the util C keyboard what we should call. We missed. So once press tab is done, okay, before this verbose print, we have to call util C keyboard. That is the actual call. Key transformation shape. Okay, so util C keyboard, that is the code that is here in util C keyboard. This is the actual keyboard code. There we are passing the key, what is the key, and transformation of the shape. So whatever shape we have now, so that shape it would modify and return back. So that is the idea. So we'll try again. Okay, so I'll change. So we are rotating across x-axis, and then we are rotating around y-axis. Okay, I think I can make it little bolder. X and y. Okay, so we'll in this program we have GL line width. So 1 to 2 I'll make. We'll try again. Okay, so axis is pretty clear. Now I can rotate along x-axis. I am pressing X. It is moving along x-axis. I am pressing Y. Okay, so these are the global. I think y-axis should be longer. It is short. So we'll change that. Okay, so we'll see the zip. Okay, in global axis we'll set the y-axis. Okay, so y. I think this is not the zip we are looking for. Okay, so this is the zip we are looking for. So minus 0.52. So we'll change this. Okay, so we'll change 0, 0.5 to 0, 0.8. Substitute 0, 0.5. Okay. $34, 0, 0. Okay, 0, 0, 0.8, 0, 0.8. Okay, so what I have done wrong, that also I took away. Okay, so 0 comma 0 0 comma 0. Okay, it is better now. So this braces I had removed by mistake. Okay, so if I press V, it is verbose message, and now the current shape is global. I can move along x-axis. Now y-axis is long. This is what we can see than earlier. Okay, so y-axis is long. It is 0.8, not ts.py zip minus 0.5 to 1 O and 1 to 0. Okay, so this should be long. We are doing some really nonsense. We'll make it 2. Okay, and we made this long, that is local axis. Okay, leave it. Okay, so y axis is long. So now I can rotate along x axis and then I can rotate. So this is the place we are. So blue is z axis and short blue is minus z axis, long blue is plus x, y. So this is the cone. Now we'll go by the exercises what we are supposed to do. So first is we'll do local coordinate. So local coordinate means I have to press control. Okay, so I'll press tab. Okay, so I think I can do it again. Okay, tab. Now I am in the cone. So here, okay, I have pressed shift G. So this is local axis. Local axis is also drawn. Now okay, okay, so we'll go with the lab. Now we have to see local axis. So in the lab, if we remember, first we have to do translation 440, then scaling, then rotation, then translation, and then, so that is the idea. So we'll go. So first we'll do 440. So we'll do up. Sorry. Okay, I'll shift to cone mode. It was in global axis mode. I have pressed the tab. I am in cone mode. Cone mode. Now I can move up 2, 3, 4, and then right 1, 2, 3, 4. Okay, so it should draw, the idea is should draw the local axis. It is not drawing. If I see my code, then when it is drawing in the shape, if local coordinate is local, coordinate system is local, then we have to draw local axis line width 2, and then we have to draw local axis in these colors. Okay, GL line color I and 1, but it is not drawing the way we want. Okay, let's find out. Okay, we are in local mode. Okay, so it should draw the local axis. Okay, it is rotating across local axis, but drawing is not happening of the local axis. If L shape equal to cone, coordinate system equal to local, is it local? tab V. Okay, so we can print this X. I'm sorry. Okay, so we'll see the dev keyboard. What's going on? I'm pressing G. Okay, if I research G key decode, coordinate system G should equal to grand if key or decode is G, else it should be local. Okay, we'll print coordinate system what it is to debug it. Okay, so we are printing coordinate system also, because if it is local it should draw coordinate system equal to, we'll try again. Okay, now I am pressing capital G and V. Okay, coordinate system is grand. If I press small g, still grand. So it is not taking what I want. So there is a problem. Okay, coordinate system G is grand. Coordinate system G. Coordinate system G. Coordinate system G. Okay, so we did typo. This is problem little bit in coordinate. Okay, now it should be okay. Okay, so now I'm pressing G, it's local coordinate. Now we'll go by the lab. So we'll move 4 4 4 4. Okay, where we are, stay in global. I'll press tab G. Okay, so local coordinate system is grand. Okay, so if I press capital G, then it is coming to local. This is not what I want. Coordinate system is grand. Okay, small g, and local is capital G. Okay, fine. Okay, so we'll do like that only. So we move like this, and G, and okay. So we can see that local coordinate system has come up. It is in local mode now. If I press V, it is in local mode now. Okay, so press down and we'll come to that location only. So 4 idea is it should move 4 up and 4 right. 1 2 3 4. 1 2 3 4. Okay, now it should scale. I press S, scaled. Okay, now it should rotate. So I rotate. So my shift Z. Okay, so I rotate along Z axis. So I can say Z 2 3 4 5 6 7 8 9. Okay, so if I press V, then it rotated minus 90 degree. Then I would scale in y direction. Okay, so y axis is not clear much, so that we have to see. So 5, so y means up, 1, 2, 3, 4, 5. So this is what we are getting, the final in local coordinate system. So I can kind of bring back these guys. Okay. So this is what we have drawn here. In the lab exercise. This is exactly like this. Okay. This is exactly like. So this is we got through local coordinate system. Now in grand coordinate system it should happen in reverse way. So I'll repeat this local coordinate system again. Okay. Now I'll go to local coordinate system. Now it has its own axis. I'll move up, right? So that came to 4 size. Then I'll scaled. Then I'll rotate along z axis. Then I'll move along y axis. So that is up. So it came here. So this is a local axis movement. The way we described it happened in that way. Okay, we can see through this view also where it is. If I have x, y, z all three visible, then it should look like this. Okay. Now we'll see why y-axis is not z. X is 0.5. Okay. So while y will make it 1.0, so y should be visible more. Okay. So we'll execute and we'll keep it. I think. Okay, okay, local axis came. Then scaling, then rotation. Then 5 times in y direction. So if I say up, it is going in y direction. So this axis has no meaning now, whatever we see. If I press up, so initially if I press up, it was going in y direction. If I press up, then again it is going in y direction only. So new axis has come effect. Now if I press x, if I press right, then this is right. This is the new axis. This is x is right. This is x is left. This is y forward and y backward. So if I press right, it will go in x direction. Okay, left. If I press up, it will go in y direction. Okay. Now, okay, so we will code for the for showing up this fixed grand coordinate. Okay. So this is fixed grand coordinate. So in fixed grand coordinate, we'll reverse it for x in reversed transformation L shape. If coordinate system G equal to grand, S transformation L shape. Okay, so this is the code we have added. So for the grand coordinate system, we are making reverse. Whatever the transformation we got, so it is reverse. Okay, so this is top to down, bottom, and in grand it is bottom to top. Okay, so we'll do the computation reverse. In code, in actual code, whatever happens that we have showed you. So now we'll make it reverse. So reverse transformation L shape. If coordinate system is grand, S just so there is no reverse. So reverse is here. Okay. We'll try now. We already have for the local coordinate, so there won't be any coordinate here. Okay. Now, so this is grand coordinate, so there won't be local axis. Now, idea is to move from the back side. Okay, so we'll translate first 5 times 1, 2, 3, 4, 5. Then we'll rotate 90 degree. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it rotated along Z axis. So this is the difference. There it rotated along its own axis. Here it rotated along the Z axis. Now we'll scale. It is scaled. Now we'll move 4 up and 4. So if I say up, then it is going in real up. There is no local axis here. Okay. So this is up. 4. Then right. Both are exactly same. Okay. So both are exactly same. Only idea is that we take which approach. Okay. I'll show it again. Okay. Now I'll press tab. It will go to cone mode. Small g, it going to grand coordinate mode. Then we'll first translate. Okay, first we'll translate 1, 2, 3, 4, 5, and then rotate. Then scale. Then 1, 2, 3, 4, and right. Okay, so both are same. Okay, so this is okay. So I can do it for a local axis again. Now I move to cone mode. I press tab. Grand coordinates. Now we have local. So local axis has come up. Now we'll go from top to bottom. In local we'll go top to. So first we'll translate 4, 4. So I'll see if it really local. I pressed V. Oh, it is local. 1, 2, 3, 4. Right. 1, 2, 3, 4. Okay. Please mind that this global axis X and Y is gone. There is no meaning of X and Y. And now this local axis has come into the picture. Then top to bottom. Then scale. Scale. Then rotate. It will rotate along its own axis because that is the new axis. Okay. Now we'll translate. So if I press along y axis, that is up, it will go in new y-axis, not in the grand y-axis. Grand y-axis is going this direction. New y-axis is this. So I'll press 5 times. 1, 2, 3, 4, 5. Okay. Both should be exactly same. You can see I am just bringing the one window by pressing exactly same. Okay, this is the way how we compute. Okay, so we'll move to next lab session. Okay, so ortho projection and perspective projection. So there is a difference. That is the idea. Okay, so we can bring the where they are. Okay, so they are at same point. Okay, so we'll close this, and now we will bring the perspective real. Right now it is perspective only. So it doesn't matter. Okay, so we'll go with this. So we'll make right, and we'll go far. It is becoming small. I can show where we are, and we'll go up. Okay. Now I can show where we are. Okay, so this is not the lab we want to do. Okay, so we'll try again what we want to do in lab. So okay, so first we'll come to the will be in global only, and we'll rotate this. Okay, now we'll move it right. We'll move it. You can see this cone. It should be, if I bring down and left, it is a round. But if I move right, this is perspective. Then I'll press far. It is changing. If I press near, it is coming near camera. Size is growing. Size is decreasing. That I can show here. It is like this, or it is like this. Okay. Now we'll go with the orthographic. Same thing. Exactly. Now it is ortho. Okay. 90 degree. Nothing. No cone shape. We can see it's still sphere. Okay. Now I am pressing far. It is going far. No change. This is perspective. Sorry. Okay. I think this was the original. Okay. So both are different. Same we have drawn. I think y like this. Okay, so more or less it is same, but drawing is different. It can be seen. So it is far. So even it is far, but it is big, it is a small, and it did other kind of drama also. So I think I can bring, okay. So both are different. Left side is ortho and right side is perspective. So this also makes the change. Okay, we'll go with another one. Okay, how viewport makes the difference. So whatever we are seeing, that is 0, 0 and WH. Okay, we'll try another viewport. Okay, we'll bring back ortho and viewport will modify. Now the first slab session is this in W by 2, in W by 2, sorry, in W by 4, 0 int W by 2 H. So width we are, okay. So X we have shifted by 4, Y is 0, H is 0, and width we are decreasing, height we are keeping same. Certainly it is different. So whatever we used to get is different. So this is the original. This is the original. This is what we get. So we make the width smaller and height bigger. So it changed. Now we'll make, okay. Now we'll keep it as 0 and height will change. I think that is the code. Okay. H by 2. So height is int H by 4 and width is same. Okay. So height we are decreasing, keeping width same. Okay, it is different. Okay, so this is the lab session. GL port, if we change, then it is changing. Okay, so this is all about transformation stages. I have another example. I have one aeroplane. I'll copy it here. Now I have three files, aeroplane.obj, and now we'll change. Now we'll change this cone to airplane, and we'll have one airplane equal to none. Here we'll have global airplane, and here we'll instantiate airplane. Anything we can give, there is nothing like that. And here now we, instead of L-shaped cone, now we have L if L shape equal to airplane. Color of airplane will keep kind of green. So we'll have GL color 3F, and we have airplane dot display mode equal to something like this. That's it. So airplane should come now. I think GL pop matrix would come here. Okay, so we'll come back to original, that is GL viewport. We'll try now. Oh, so Mr. Aeroplane has arrived and we can see actually where it is. So aeroplane is on Z axis and its nose is at origin and its up direction is Y axis, left and right wing is X axis. Now I'll press Ctrl G and will proceed in a local coordinate. Now if I press next, then next means it would come near the camera in Z, positive Z direction. It is coming. Okay. Now I can rotate. If I press next, it would go in Z. Z direction is modified. Okay. Now if I rotate Y axis, so this is the plane. Here it is. And if I rotate across Z axis, sorry, I think I rotated wrongly. Okay, so probably we'll do in bigger picture. Okay, so this is the plane and here it is, and now we'll move it to front. We'll rotate it, and if I press next, it would go in this direction. I can rotate it back. Now it is on X axis. I can see it. Okay, this is like this. Now I can again rotate. So it is going on to take off, and okay, so it is on runway. So we'll rotate again. So it is ready to take off and it is on XZ plane, this aeroplane, because we have not shifted up or down. I can shift it up and down, up and down. Okay. Now it is ready to take off. So it will proceed. Now we will rotate along okay, X-axis. Okay, it is flying here. Okay, nice. I can rotate it again to kind of land. Okay, so if I press next, oh, it is in mode to land. And if I press X, okay, so it is landed. It is horizontal to x-axis or not, so that we can see. So I can rotate it back y-axis. Okay, it is really horizontal. Okay, so I can bring it down. So this is Mr. Aeroplane. Now we can have two aeroplanes. I have aeroplane 1 and airplane 2. Airplane 1, airplane 2. Airplane 1, airplane 2. Now we can instantiate twice. Airplane 2, airplane 1. Pretty easy. And here I can just make it L shape equal to airplane 1, airplane 1. I can just do copy paste. So kind of 3y, just paste it here. Aeroplane 2 and aeroplane 2. Okay, so color we can make it kind of purple. So one plane is green and one plane is purple. That's it. No other change is required. We can try. Oh, so there are two aeroplanes. Now, there are two aeroplanes. Okay. Now one aeroplane I'll move. So green is moving. And it is ready to take off. So it will go. Okay. Probably I rotated much. And I can rotate now so that it can take off. Okay, so it is proceeding. Now, okay. Okay. Now, next aeroplane is ready. Okay, so now it will take off, so we'll rotate it other way. Okay, nice. Now it will tilt. Press wrong key. Okay. Now it would fly. Okay. So these are two aeroplanes. We can see one this side. Now I can rotate the axis and we see what it is. So these are here, and I can rotate it back. So now z-axis is perpendicular uh, to the camera. So these planes are here actually. Okay. So this is how we can have local local coordinate movement. Okay. So okay, so we covered the pipeline and then rotation across line, then grand coordinate, fixed coordinate, moving local. This is what we showed now. And projection matrix, perspective division, then viewport. Then in lab session we showed this. Now we have the flying aeroplane. Now we can actually kind of move next. It is actually going away. Another one is also. Another one can take even more steep. Okay. If I rotate, it would come back. Okay. Now I can have, I think, okay. If you are looking for Kiwi or machine learning training, or you are looking for Kiwi and machine learning application development, or you are looking for porting your QTQML application to Kiwi, or you are looking for 3D OpenGL application development, you can contact us. You can also sponsor our videos. Please do contact us.